Ever notice how the Bambu AMS seems to know how much filament is left on a spool, even if it's half used, or not on a bamboo spool at all? There's no scale, no camera watching the roll, so how does it actually work? Before we talk math, let's talk hardware. Here's an overview of the AMS sensors, and we'll highlight the ones that matter for these calculations. Each AMS slot has a feeder motor that actively drives the filament forward. This is what controls filament motion through the system. As filament moves, it passes the filament odometer near the AMS exit. This sensor tracks how much filament has physically moved through the system. Think of it as a distance counter. It knows length, not weight. The spool itself sits on motorized rollers, which rotate the spool as filament is fed or retracted. These rollers don't measure filament directly, but they enable controlled spool rotation. Finally, on supported spools, an RFID tag is detected by the RFID reader once per spool rotation. The tag identifies filament type and color. It also acts as a rotational reference point, something the AMS can count against filament movement. Everything else in the AMS exists to support feeding and routing, but these components are the ones that make the estimation possible. When you insert filament into the AMS, the process is very deliberate. First, the slot feeder motor pulls it in slightly and the filament sensor detects its presence. The spool is then rolled to take up some slack and establish a known good starting position. This ensures the filament is seated correctly and ready for controlled feeding. If you're running a bamboo spool, once the check process is complete, you'll see filament color, type, and an approximate remaining amount on the screen, in the app, and in the slicer. But how does the AMS arrive at that estimate? Functionally, what the AMS does is the electronic version of one of these basic feeler gauges, a relative gauge based on motion and reference rather than distance to the edge of the spool. The limits of that accuracy are worth understanding, and we'll get to that later in the video as well. So let's visualize this process like a third grader with a box of markers. As our filament enters the system, it'll hit the feeder drive and the filament presence sensor. As we proceed through the path, we next come across the filament fed sensor. Notice its position just before the other AMS slots merge into the path. As we continue through the journey, our filament finds the odometer roller. Although we can now sense the motion, we cannot yet start counting. We have to let the filament continue to feed until the RFID sensor senses the tag. Now that we have the RFID sensor tripped, we know our 0 point. We can now start counting the odometer readings. These reference distances are fixed in firmware, but a lot of things can trip this number up. We'll talk about those potential issues a bit later as well. We get to the 10 count as the RFID tag trips the sensor again. Brand new spool, perfect. One rotation, exactly 10 counts. Skipping all the boring beginning part again, let's swap this spool with one that has 600 grams remaining instead of being a full 1 kilogram. We're at the point where the RFID tag is tripping the sensor and we're ready to start measuring. The filament starts to be fed and the odometer rolls. A partially used spool that has smaller diameter means that it will spin slightly faster. The RFID comes back into alignment while our odometer is on the number 6. On our base 10 easy math scale, that means that we have about 60% of a spool remaining. As our filament retracts to the resting state, let's explain the math that ties rotation filament length and the remaining spool size together. I have a known value, like 1 rotation. I also know how much filament is pulled during that 1 rotation. I can do some division and figure out the circumference of the filament on the remaining spool. Notice that the filament retracts to just before the filament fed sensor. This is why that sensor is placed before the merge point. As long as it's not tripped, it gives the AMS a known safe starting position so other filaments can share the same path and odometer without obstruction. Logic explains why reusing an RFID tag on an aftermarket spool still works. The RFID tag isn't storing remaining filament. It only acts as a rotational reference point. The length per rotation math adapts to the physical spool. What does not adapt is the metadata. An aftermarket spool will still be shown as the filament type and color associated with the original RFID tag. This system is smart, but it's still an estimate. There are 2 main categories of limitations to keep in mind. First, geometric assumptions. The math assumes a roughly standard spool width and reasonably even winding. Unusual spool shapes or very uneven layering will affect how much filament is released per rotation. This will skew your numbers. Next, mechanical realities. The AMS can't see tangled layers, or filament that slips on the spool during feeding. All of these can cause an estimate to drift slightly. This is why Bambu calls this an estimation, not a measurement. You won't get down to the gram, just a reliable sense of about how much filament remains on a roll. So the AMS isn't guessing. It isn't using magic either. It uses rotation as a reference, filament length as a measurement, and combines the two to estimate what's left on the spool so you can print confidently even when you're not standing next to the printer looking at the AMS. Check out this playlist to learn more about how your printer works.
The silent genius under plastic skin, watching every rotation like it's counting wins. Reads that tag on the rim, knows the brand, knows the weight, puts the data in place, then it estimates.